Okay, folks, good morning. Good morning. Let me, before I forget, share my screen. And let me go here. In fact, let me go here. And, oh, actually, not that. Okay, so the last time we were here, hold on 1 minute. Okay, so the last time we were here, we were working out the questions in assignment number 4. And maybe I'm wrong, but I think we stopped. Did we do question 15? Can anybody tell me? I don't remember, to be perfectly honest. Oh, we didn't do number 14. Oh, okay. Okay, so number 14 is what we're going to do right now and proceed from there. So in the case of number 14, the question says, find the pH of a 0.065 m solution of formic acid. The acid dissociation constant Ka for formic acid is 1.8 times 10 to the minus 4. So this acid is a relatively, among weak acids, it's a relatively strong acid, all right? 1.8 times 10 to the minus 4 is one of the larger values for Ka. Okay, so let me scroll down a bit. So the first thing I would do is, oh, shoot, hold on. I need to get my pen working. All right, so the first thing I would do is I would determine I'll write down the expression for the dissociation of the weak acid. Now, it is not really important for us to write down the entire formula for the acid. Okay, why is my pen not working? Hold on 1 minute. Okay, now it's working. Okay, so it's not really important for you to write down the entire formula for the acid. So I'm just going to use HA to represent the acid, all right? So when that dissociates as a weak acid, it forms H plus and A minus, all right? So what I would proceed to do now is draw an ice table. Remember, I stands for initial change and equilibrium. So the initial concentration of the acid is 0.065, and that of the H plus and the A minus would initially be 0. The change would be minus X for the acid and plus X respectively for H plus and A minus. So at equilibrium, the concentration of the acid would be 0.065 minus X, and X here for H plus and X here for A minus respectively. So Ka is going to be equal to the concentration of H plus times the concentration of A minus, all divided by the concentration of HA. And these are all equilibrium terms. So that means that we can place these terms into this equation. So for H plus and A minus, it's X each. So when you multiply them, you're going to get X squared up top as the numerator. And below, you're going to have 0.065 minus X, all right? So again, if you remember what we did before, we make an assumption, because it's a weak acid, that X is much less than 0.065, which means that 0.065 minus X would be approximately equal to 0.065. So that simplifies the Ka expression to be equal to X squared over 0.065, which means that X would be equal to the square root of Ka times 0.065 And the Ka value is given as 1.8 times 10 to the minus 4. So multiply that by 0.065. And we find the square root of all of that. Now, let me see, because I didn't do this before today. So let me see what this gives. 1.8 times 10 to the minus 4 times 0.065. So according to my calculations, and again, please do these calculations yourself to check to make sure that I'm doing the right thing. But according to my calculation, the answer here comes out to be equal to 1.2 times 10 to the minus 5. All right. And then now, of course, we need to find the percent dissociation to test to make sure that our assumption is valid. And in order for us to do that, we're going to take the 1.2 times 10 to the minus 5 divided by the initial concentration, which is 0.065. So these are both concentrations, molarity. We multiply that fraction by 100. So let me do that now. 1.2 times 10 to the minus 5 divided by 0.065 times 100. So according to my calculation, this works out to be equal to 0.018%. So that means that the assumption is valid. So all I have to do now is to find the pH. So therefore, the concentration of H plus would be equal to 1.2 times 10 to the minus 5 m, which means that the pH will be equal to minus log of 1.2 times 10 to the minus 5. And let's see what that gives, 1.2 times 10 to the minus 5. Find the minus log of that. So according to my calculation, this works out to be equal to 4.92. And that would be the answer. All right. Okay, any questions about this particular solution? Any questions? Any questions about this?
When I typed the square root into my calculator, I got 3.4 times 10 to the third or negative third.
You're talking about this part here?
Yes, I don't know if it's my calculator or.
Let me do it. Yeah, it could be me. It could be me. Let me do it again. 1.8 times 10 to the minus 4 times 0.065. Oh, it's me. I forgot the square root. So
Professor Nicely.
Uh-huh.
I think this is a repeat problem of number 8.
Oh, it is?
Yeah.
Let me check. Number 8. Number 8. You're absolutely right. And we did do that one. Yeah. And yeah, we did do right. So this is number 8. So you guys should have the solution for that already. So I won't go through this again. Thank you. Whoever said that. I don't know. I wasn't following who was talking a while ago, but whoever said that, thank you very much. Okay, so let me get rid of this here. Let me clear this and do this and scroll down. And scroll down to number 15. Okay, so number 15 says you are to find the pH of a solution that contains, okay, so in this case, there are 2 acids in the same mixture. One of them is lactic acid, and it gives you the Ka for that one. And the other one is propionic acid, also known as propanoic acid. And it gives you the Ka for that acid as well. It gives you also their separate molarities. So let's see, how shall we tackle this? Well, I would say the overall strategy that you would take in order to solve this one is to determine the concentration of H plus produced in each case, and then add those 2 to give you the total hydrogen ion concentration, and then find the minus log of that value, and that will give you the pH. So it's very similar to what we just did a while ago, but we're going to do it to 2 acids, right? So let me, I think I'm going to need some space for this one. Let me see. Yeah, I'm going to need some space for this one. So I'm assuming that you guys would have pulled up this particular assignment, and therefore you'll have access to it so you can refer to it. So what I'm going to do is I'm going to go to my, hold on. I'm going to go to, why can't I see it down here? Hold on 1 minute. Okay, something, let me, okay, I don't know what's going on here, folks. I apologize for what's going on here, even though I don't understand. Okay. Okay, and okay, now we're in business. All right, so let me get rid of this here. Okay, so the question says, let me just write down the essential information that is provided in the question. The question gave you lactic acid. I'm going to use HA to represent lactic acid, right? So Ka for lactic acid is going to be equal to 1.4 times 10 to the minus 4. And the concentration of lactic acid initially is equal to 0.0034. And for the other acid, which is propanoic acid, I'm going to call it HB. And the Ka for that is equal to 1.4 times 10 to the minus 5. And the concentration of HB, according to the question, is equal to 0.056. All right. And what the question is asking for is the pH. All right. Okay, so what I would do first is start off with the lactic acid, H plus A minus. All right. And initially, the concentration of the lactic acid is 0.034, I'm sorry. This will be 0, that will be 0. The change here would be minus X, that will be plus X, and that will be plus X. And at equilibrium, you're going to have 0.00034 minus X, and this will be X, and this will be X. So that means that Ka will be equal to X squared over 0.0034 minus X. Again, we're going to assume that X is much less than 0.0034, which implies that 0.0034 minus X is approximately 0.0034. So therefore, Ka will be equal to X squared over 0.0034. So we can say that X will be equal to the square root of Ka times 0.0034, which would be equal to square root of 1.4 times 10 to the minus 4 times 0.0034. So let's see what that works out to give. That gives 1.4 times 10 to the minus 4 times 0.0034, and then square root. So according to my calculations, this works out to be equal to 6 point, how many sig figs? 2 sig figs. So that's 6.9 times 10 to the minus 4. So now what we have to do is find the percent dissociation. So the percent dissociation is equal to 6.9 times 10 to the minus 4 m divided by the initial concentration, which is 0.0034, 0.0034 M times 100%. And based on my calculations, this gives, let me see here, 6.9 times 10 to the minus 4 divided by 0.0034. Okay, now this one, according to my calculation, this works out to give 20%, which is obviously greater than 5%, which means that the assumption is not valid. All right? So if the assumption is not valid, now remember the assumption we made, let me write this down, assumption not valid. If the assumption is not valid, that means that this is not true, right? And if this is not true, that means that we have to go back to this equation and solve it the longer way, all right? So let me see if I can do that down here. So we're going to go back to Ka, which is 1.4 times 10 to the minus 5 is equal to x squared, which is above here, divided by 0.0034 minus x, all right? And then we have to do some algebraic rearrangement, which I won't go into all the steps. I leave you guys to figure that out. I'm just going to jump to the quadratic equation that results from that. And that equation will be x squared plus 1.4 times 10 to the minus 4x minus 4.8 times 10 to the minus 7, and that is equal to 0. And if you were to solve for x, you're going to get two possible values. One of them will be 6.2 times 10 to the minus 4, and the other one will be minus 7.7 times 10 to the minus 4. So of these two, which one would you choose as the actual value for x in this case?
Positive one, 6.2
Exactly,
times 10 to
right.
the minus 4.
So basically, you're going to use 6.2 times 10 to the minus 4 and ignore this one because you cannot have a negative concentration. So therefore, the concentration of H plus from HA will be equal to 6.2 times 10 to the minus 4 M. All right? So that's basically the concentration of H plus from HA. Now we need to do something similar, very similar, in the case of HB, which would be the propionic acid. All right? So I'm going to need some more space. Maybe I can cheat a bit. But before I move on, any questions about all that I've done here? Any questions? Any questions? Okay, so what I'm going to do here is erase this right here and replace it with the initial concentration. Well, let me just, to avoid confusion, let me just erase the A's here and replace those with B and B minus, all right? So that means that the initial concentration here would be the 0.056, 0.056. And then down here, I'm going to erase this here and put 0.056 minus x, all right? So the change will continue over here. And here as well. Let me just erase this here. And also here. And also here. So in each of these cases, I'm going to replace it with 0.056 minus x. This will be 0.056. And this will be 0.056, and this would be 0.056. So that means that down here now, I'm going to have also (0.056). So that means here now is where I'm going to, whoops, eraser. I'm going to erase this here, and I'm going to put 0.056 here as well. 0.056 here. And then here is where there's going to be another change, because the Ka value we're going to use here is 1.4 times 10 to the minus 5. And I'm going to replace that with 0.056. So here, whoops, we're going to have minus 5 here. And here we're going to have 0.056. So let's see what that gives. 1.4 times 10 to the minus 5 times 0.056. And then let me find the square root of that. And the answer I got will be, let me erase this here. So the answer I got will be 8.9. Write this down. So here I'm going to put 8.9 times 10 to the minus 4. 10 to the minus 4. All right. So again, we need to find the percent dissociation. So let me erase pretty much all of this here. So to calculate the percent dissociation, that would be equal to 8.9 times 10 to the minus 4 divided by the initial concentration, which for the formic acid is 0.056 times 100%. So let me erase this right here. And according to my calculation, this works out to be equal to 1.6%. So 1.6% would be the result, which is obviously less than 5%. So for the second acid, that assumption would be valid. So assumption is valid. All right. So we can therefore say that, let me erase all this here. We don't need this anymore. So we can say that the concentration of H plus from the second acid, which is the propanoic acid, is equal to what we got here, which is 8.9 times 10 to the minus 4 m. So therefore, all we have to do is add those two. So the total concentration of H plus, which is what the question needs before we can get the pH, will be equal to the 8.9 times 10 to the minus 4 m plus the 6.2 times 10 to the minus 4 m. So when we add those two together, the answer I got is 1.51 times 10 to the minus 3. And therefore the pH, let me do it over here. The pH of this solution will be equal to minus log of 1.51 times 10 to the minus 3. And according to my calculation, this works out to be equal to 2.82. And that would be how that is done. All right. Okay, any questions about this one? Any questions?
If you were to take the concentration from each one and figure out the pH individually and add that together, would you get the same answer?
No, that would be incorrect.
Okay.
You have to do like what I just did. You have to find the total concentration of H plus by adding them together, and then find the pH of that total. All right. Okay. Good question. Any other questions about this? Any other questions? Any other questions? Any other questions? Okay. So let me minimize this here and go back to the assignment and scroll down. Okay, now this one is an interesting one, all right? It talks about ascorbic acid, which is the same thing as vitamin C. And it gives you the formula of the acid. And it says, what is the pH of a 0.10 M solution? Now, the thing about this acid is that these two hydrogens can be lost to water, right? When you add it to water. So you have two dissociation constants. This is the first one, and this is the second one. And one thing I should say, which you should have observed when you watch the videos, is that when it comes to polyprotic acid, which is what we're talking about here, meaning acids that can lose more than one proton, the Ka value for each dissociation decreases with the removal of each hydrogen ion, all right? So that's why you see that this one here has a higher value compared to this. And the reason is very simple, because in the first case, if you have, and I'm going to use HA again to represent the dissociation. So in fact, I'm going to use H2A because there are two hydrogen ions that will be released. So this is the equilibrium for the release of the first hydrogen ion, right? And Ka1 would be the dissociation constant for that. And then for the second hydrogen ion, this is the equilibrium. And that's Ka2, whoops, Ka, right? So basically, Ka2 is going to be less than Ka1. And this is pretty much universal without any exception, all right? And the reason for that, as I was about to say, is that in the case of the first dissociation, you're removing a hydrogen ion, which is positive, from something neutral, right? But the second dissociation involves removing another hydrogen ion from something which is negatively charged. And as you can imagine, that is difficult. That is more difficult, more challenging, more energy would be required for that, right? So therefore, as a result, the Ka2 value would be less compared to the Ka1 value, all right? So in this question, they gave you the pH and they gave you the two Ka values, or actually they asking for the pH, I'm sorry. They gave you the molarity of the acid and they gave you the two Ka values, all right? Okay, so what I'm gonna do again is go back to my, let me get rid of this here. I'm gonna go back to my tablet again. So let me get out of this here and let me get rid of that. Okay, so hold on. All right, so this one is a bit more complicated compared to the others, all right? So let me proceed by writing down what I just showed you earlier. I'm going to write down the equations for the dissociation. So the first dissociation, as I said before, is H2A to form H plus A minus, HA minus, I'm sorry. And the Ka1 value for that dissociation is equal to 7.9 times 10 to the minus 5. And then for the second dissociation, HA minus to form H plus and A2 minus, the Ka value for that would be, Ka2 would be equal to 1.6 times 10 to the minus 12, 1.6 times 10 to the minus 12. All right, so the idea is to find the pH of the solution. So what we're going to do is start off with the first dissociation, H2A to form H plus HA minus And I'm going to, of course, construct an ice table for this, where the initial concentration of H2A is 0.10. This is going to be 0, that's going to be 0. And just like before, change here will be minus X, change here will be plus X, change here will be plus X, all right? So at equilibrium, you're going to have 0.10 minus X. Here you're going to have X, here you're going to have X. And then we're going to say Ka1 is equal to X squared over 0.10 minus X. Again, we're going to assume that X is much less than 0.10. So that means that 0.10 minus X is approximately 0.10. So this equation will simplify to Ka1 is equal to X squared over 0.10, which implies that X is equal to the square root of 0.10 times Ka1, which is equal to square root of 0.10 times 7.9 times 10 to the minus 5. So according to my calculations, this works out to be equal to 2.8 times 10 to the minus 3. 2.8 times 10 to the minus 3, all right? So that would be the X value here, and that would be the X value here, all right? Again, we need to find the percent dissociation to make sure that the assumption is valid, which I think it is. Let's see here, 2.8 times 10 to the minus 3 m divided by 0.10 m times 100%. And according to my calculation, that works out to be equal to 2.8%, which is obviously less than 5%. So that means that assumption is valid. All right. Okay, so with that out of the way, we can therefore basically use this value here as representing the concentrations of not only H plus, but also the HA minus at equilibrium for the first dissociation. But remember now, there's a second dissociation, right? Let me see here. But before we do that, let me just make a note here, and that is that the second dissociation is basically going to be negligible, all right? And we can say that safely because the percent dissociation for the first dissociation is less than 5%. So we know therefore that for the second dissociation, the percent dissociation would be even less than the 2.8%. So therefore, we can simply take the concentration of H0 plus to be equal to 2.8 times 10 to the minus 3 m. And therefore, we can say that the pH of the solution is equal to minus log of 2.8 times 10 to the minus 3. And according to, whoops, let me erase this here. Make this a bit more presentable. So this would be minus 3. And that works out to equal to 2.55, 2.55. All right, so that will be the pH of the solution. All right. But the question is also asking for the concentration of the second conjugate base, meaning, whoops, why did I do that? Okay, so the question is asking for the concentration of, oh Lord, okay. The question is asking for the concentration of A2 minus, all right? So we know what the pH is, but now the question is asking for the concentration of A2 minus, I'm sorry. So what I'm gonna do is, okay, what is going on here? Okay, I'm going to clear this, but I want to make sure that you have this down. So let me know when you're through with this, folks, so I can clear this because I'm going to need space for answering the other part.
I have a question.
Yes, ma'am.
Under the second dissociation is negligible. Where did you
Mm.
get the concentration of H3O plus?
Oh, I'm sorry. H3O plus is the same thing as H plus, which is the X that we calculated right here.
Okay.
Right. You know, sometimes I switch to H3O plus instead of writing H plus. It's the same thing. Okay, any other questions? Any other questions? Is it okay for me to clear this now?
Yes.
All right. Okay, so now we need to find the concentration of A2 minus, right? So in order for us to do that, what I'm going to do is write down this expression here for the Ka2. Well, let me remind you what the second dissociation is so that we have it to refer to. It's HA minus to form H plus A2 minus, right? And the aim is to determine this. So Ka2 will be equal to the concentration of H plus times the concentration of A minus divided by the concentration of HA minus, all right? So oh shoot, you know what? I should have done the ice table first. So let me erase this, I'm sorry. Let me do the ice table, because the ice table is kind of important in this context. Okay, so based on the results of the first dissociation, the concentration of A minus is going to be equal to, hold on. The concentration of A minus is going to be equal to X from the first part, which is 2.8 times 10 to the minus 3. And the concentration of H plus is also going to be the same, 2.8 times 10 to the minus 3. And the concentration of A2 minus would be 0, all right? So what we're going to do now is look at what happened as far as the change is concerned, because these would be the initial concentrations in this new ice table. So the change here would be minus X for the HA minus, plus X for the H plus, and plus X for the A2 minus. So at equilibrium, you're going to have 2.8 times 10 to the minus 3 minus X. For the H plus, you're going to have 2.8 times 10 to the minus 3 plus X, and here you're going to have X, right? So we can write down that Ka2 is going to be equal to, as I said before, the concentration of H plus times the concentration of A2 minus divided by the concentration of HA. And then we put in HA minus, I'm sorry, and then we put in the different terms. For H plus, it's going to be 2.8 times 10 to the minus 3 plus X multiplied by X divided by 2.8 times 10 to the minus 3 minus X, all right? So the whole aim, and this will be equal to Ka2, which is equal to, what was Ka2 equal to? Ka2 was equal to 1.6 times 10 to the minus 12. So let me put that here, 1.6 times 10 to the minus 12. So basically from here, we need to solve for X. Now we can simplify things a bit because basically X, we can assume that X is small compared to 2.8 times 10 to the minus 3. We can assume that because we assumed in the first dissociation that X is small compared to the initial concentration, which is 0.1, and we found out that the percent dissociation is less than 5%. So we don't even need to calculate the percent dissociation for the second dissociation because we know that this will be even less than what it was before for the first dissociation. So basically, as a result of making this assumption, this equation is simplified to get 2.8 times 10 to the minus 3 times X divided by 2.8 times 10 to the minus 3 equal to 1.6 times 10 to the minus 12. This will cancel with this, so therefore you're going to end up with X being equal to 1.6 times 10 to the minus 12, and that would be equal to the concentration of A2 minus, which is right here, all right? And that would be the answer to the second part of the question, all right? Okay, any questions about this one? Any questions? And don't forget the units M for that. Any questions? Okay, so let me go back to the assignment and move on to question number 17. And 17 says, calculate the pH of a solution that results when 40 mils of 0.100 m ammonia is diluted with 20 mils of distilled water. So let's hear your ideas about this one. How would you go about solving this one? Anybody? Somebody? They gave you the volume, they gave you the molarity, and the question says you're adding 20 mils of water to this solution. So what would be the first thing you would do in order to get the pH of the resulting solution?
Would you use the dilution formula to calculate the second molarity?
Very good. So let's do that. Hold on. Let me bring my pen here. Okay. So how would you do that?
You would do the 0.1 times 40 is equal to 20 times M2 and then solve it.
Hold on. Let me hear what you just said.
Would you do 0.1 times 40
Times 40.00
is
mils.
equal to 20 times X, which would be M2?
You sure about the 20?
Oh, it would
What?
be 60.
Exactly, 60.0 mils times the new molarity, which would be M2, all right? So that means that you'd have to divide both sides by 60.0 mils to get M2. And according to my calculation, that works out to be equal to 0.0667 M. Okay, so now that we have done that, what's the next step?
Would you set up an ice table with the new concentration?
Okay, so what would be the equation under which you're going to set up the ice table? Because you have to make sure you get that down first before you have the actual ice table. What happens when ammonia is added to water? What's the equation?
NH4 plus
NH4 plus.
plus OH negative.
Okay, very good. So, setting up the ice table. So initially we're going to have 0.0667 here. Here you're going to have 0, here you're going to have 0. The change here is going to be minus X plus X plus X. And then at equilibrium, you're going to have 0.0667 minus X Here you're going to have x, here you're going to have x, and then we're going to write down the KB expression because now we're talking about using a base. So KB would be equal to x squared over 0.0667 minus x. And just like before, we assume that x is much less than 0.0667. So that simplifies the equation to KB is equal to x squared over 0.0667. So that means that, well, let me do it on here. So x will be equal to the square root of 0.0667 times KB. Now, KB would have to be given to you, and it would be available in the tables. I think I told you where it's located. If you go to, hold on, if you go to the Canvas page, go to Files, and go to Tables, and go to where it says dissociation constant. Let me download this here. And the bases are listed below, and you see that for ammonia, make this larger. For ammonia, KB value is 1.8 times 10 to the minus 5, all right? So that's a value of KB that we're going to use here. So this would be, go back to this here. Okay, so this would be 0.0667 times KB, which is 1.8 times 10 to the minus 5. And according to my calculations, this works out to be equal to 1.1 times 10 to the minus 3 M. And of course, we need to find the percent dissociation. So that will be equal to 1.1 times 10 to the minus 3 M divided by 0.0667 M times 100%. And according to my calculation, this works out to be equal to 1.6%. So which is obviously less than 5%. So therefore, we can say that X, which is a concentration of OH minus, can be taken to be equal to 1.1 times 10 to the minus 3, all right? But of course, we cannot stop there because the question is asking for the pH. So how would you find the pH?
You would find pOH first.
Okay, so where shall I squeeze this in? Let me do that up here. So pOH will be equal to minus log of 1.1 times 10 to the minus 3, which means that pH, well, let me work that out first. So that will be equal to 2.96. 2.96, and therefore the pH will be equal to 14.00 minus 2, sorry about that, 2.96. And according to my calculation, that works out to be 11.04. So this would be the final answer. And that's how you do that. All right. Okay, any questions about this one? Any questions? Any questions? Okay, is it okay for me to clear this? Going once. Going twice. Okay, so let me clear this here. Let me do this here. And let me continue to scroll down. Now here, we're starting off with the same 40 mils of 0.100 m ammonia, but this time you're going to mix it with 20 mils of a 0.200 m hydrochloric acid solution. Okay, so this one is not as easy as the previous one, because in this case, there's an actual reaction that will be taking place where the hydrochloric acid is going to react with the ammonia. And I think I'm going to need more space. So I'm going to go back to my writing pad right here. Let me clear this here.
It's 10:51.
Oh, thank you for letting me know. I'm having too much fun. All right, let me take a break here and then we'll restart at 11 o'clock. And then we'll move on to the B part of number 17. All right, see you soon. Okay, folks, I'm back. So as you were saying, we're going to move on to 17B. Now remember, the original solution will be this right here. 40 mils of the 0.100 m ammonia solution. And to that, we're adding 20 mils of the 0.200 m solution of hydrochloric acid. So as I said before, there's going to be a reaction that will occur between the hydrochloric acid and the ammonia. So what we have to do is figure out what will remain after the reaction takes place. And based on that, we're going to determine the pH. All right. So again, I'm going to go to my writing pad here. And what I'm going to do is write down the equation for the reaction that will take place between ammonia and the hydrochloric acid. So this is ammonia. And this is hydrochloric acid. All right. HCl. So can anybody tell me what would be the products of this reaction?
Is it NH4 plus Cl negative?
Exactly. Ammonium plus the chloride. All right. So what I'm going to do here is, and I probably should have done this before, but let me squeeze it over here. What I'm going to do is find out the number of moles that is present in each solution, right? So we start off with, for the ammonia, let me do the number of moles of ammonia. That would be equal to 40.0 mils, which we have to convert to liters. So 1 liter over 1,000 mils. And then we multiply that by the molarity, which is 0.100 moles per liter. And when I do that, I'm going to end up with this being equal to 8.00 times 10 to the minus 3 moles. So initially, that's the amount of ammonia that will be present, 8.00 times 10 to the minus 3. And then I'm going to do a similar calculation for the number of moles of HCl, and that would be equal to the volume, which is 20.00, I'm sorry, mils. Again, we convert this to liters, so 1 liter over 1,000 mils, and we multiply that by the molarity, which is equal to 0.200 moles per liter. And when I work that out, I'm going to get 4.00 times 10 to the minus 3. Okay, so that will go here. Okay, now you'll notice that the type of arrow I'm using here is the arrow going in one direction, all right? And the reason why that is so is because this is an acid-base reaction. All acid-base reactions will go to completion because the hydrochloric acid is the acid in this reaction and the ammonia is the base. All right? So all of the limiting reactant will be used up, and we can easily tell which is the limiting reactant. And that would be this one right here, right? Because it's a 1-to-1 mole ratio between the two, and this one has a lower value. So what that means is that all of this would be used up. And the same amount of the ammonia would be used up. And over here, you're going to have 4.00 times 10 to the minus 3 produced. All right. So at the end of the reaction, you're going to have 4.00 times 10 to the minus 3. Here you're going to have 0. And here you're going to have 4.00 times 10 to the minus 3. And I'm just realizing something now. Oh, shoot. I just realized something. Okay. I just realized that this is covering a topic that we have not done yet. So I'm going to stop right here for this problem. I don't want to get into this topic at this juncture because how did this question end up here? Anyway, This is for next chapter, right? When we're dealing with buffers. So unfortunately, I cannot proceed beyond what we just did right here. So I'm going to scroll down. I'm sorry about that. I didn't realize that this was going to happen. Let me scroll down to see what the next question is. And I think this would be, hold on, let me see here. I think this question would be, yes, we cannot do that question either. Okay, so I'm going to stop here for now. We're going to get back to these questions when we get to the next chapter, all right? So this basically is the end of the assignment questions, all right? So what I'm going to do now is go to the PowerPoint for the next chapter. And then when we get to that particular topic of buffers, we're going to go back to this assignment so that we can complete that assignment, all right? So let me go to the PowerPoint. Did I close it? Looks like I did. Okay, so let me go here. Okay, so here, okay. So this is the next chapter, more equilibria in aqueous solutions, slightly soluble salts, and complex ions. Those are the topics that will be covered in this chapter. So let me get started with this. And the first thing we're going to talk about in this chapter is this concept known as the common ion effect. All right. So the common ion effect, as stated here, is the shift in equilibrium that is due to the presence of a common ion present in the solution, and that ion is common with one of the ions of the dissolved substance. All right. So basically, what happens in the common ion effect is that it shifts the equilibrium such that it suppresses the ionization of a weak acid or weak base if the weak acid or weak base is in the presence of the common ion. All right, so for example, let's look at this mixture. Let's say you have a mixture of sodium acetate, which by the way is a strong electrolyte. Anything that has sodium, any ionic compound that has sodium will dissociate very strongly. And then you have acetic acid, which is a very weak acid, right? So the sodium acetate will dissociate completely to form the ions, as you can see here. And the acetic acid will undergo dissociation partially to form H+ and the acetate ion. So you notice that the ion that they both have in common will be the acetate ion. So what will happen in this case here is that the dissociation of the acetate ion will be suppressed because of the presence already of the acetate ion coming from the dissociation of the sodium acetate. So what you'll find is that the equilibrium in the dissociation of the acetic acid will be shifted more towards the left. And therefore, what you'll find is that the pH of that solution would be less than the pH of the solution, would be greater actually than the pH of the solution of acetic acid by itself dissolved in water. So that's basically an example of what we call the common ion effect. So what we're going to do is look at a hypothetical situation where the weak acid is going to be represented by HA and the salt will be represented by NaA. So in this particular case, what will happen is, as we said before, the sodium salt will undergo complete dissociation and the acid will undergo partial dissociation. And the result would be as follows. We can first write down a Ka expression for the dissociation of the weak acid, and we can rearrange it to solve for H+, which is equal to Ka times the concentration of the weak acid divided by the concentration of the conjugate base of the acid. And then what we do is find the minus log of both sides. And when that happens, we're going to end up with minus log of H+ is equal to minus log of all this, which can be equated to what we have here. Minus log of Ka minus the log of the concentration of HA divided by the concentration of A-. Now you should recognize that this here, the minus log of H+ is the same thing as the pH, right? and the minus log of Ka is the same thing as the pKa, right? Now, what was done from here to here is that when you switch these two, right, when A minus becomes a numerator and HA becomes a denominator, the sign here changes from minus to plus. And then we can simply carry that down here, and we're going to end up with this equation right here. So this equation is very useful for calculating the pH of a solution of this type, where the weak acid is in combination with the salt of the weak acid in the same solution. And this equation has a special name. It's called the Henderson-Hasselbalch equation, all right? Now, there's a name given to this type of solution as well, which we're going to see on the next slide. But before we do that, so this is just basically a generalized way of expressing the Henderson-Hasselbalch equation. It is pH is equal to pKa plus log of the conjugate base divided by the concentration of the acid. Okay, so we can use that equation to solve this problem, which says what is the pH of a solution containing 0.30 m, and this is called formic acid, and 0.052 m potassium formate. So basically, it's similar to the hypothetical example that we saw before. We have a weak acid and we have the conjugate base of the acid, which comes from the potassium formate. So it's all a matter of setting up your ice table, which, to be perfectly honest, is not necessary, but I'm just going to go through this anyway, right? So this would be the state of affairs at equilibrium, and then we plug in these two terms into the equation. But of course, we assume that X is small. And for most of these problems, you don't have to test the assumption. You can simply go ahead and assume that X is small, and then we plug the concentration values into this term along with the Ka value, which of course you'd have to get from your table. So they did this already. In fact, what they did was find the minus log of Ka, and that works out to be 3.77. That goes here, and we put the two concentration values for the formate and the acetic acid here and here, and then we just do the math, and we get the pH of this solution, which in this case turns out to be 4.01, all right? So as I was saying, you don't really need to do all this here to determine the pH of the solution. All you have to do is plug in these values, all you have to do is plug in this value and this value into these two terms right here and find the pH, all right? And that's basically how we use the Henderson-Hasselbalch equation. Okay, so this type of mixture that I just described, we call it a buffer solution, or in some textbook, they simply call it buffers, right? It's a solution that is made up of either a weak acid or a weak base and the salt of the weak acid or the weak base. So in other words, if you're using a weak acid, you're going to use a salt of the weak acid along with it. Or if you're using a weak base, then you're going to use the salt of the weak base, all right? So that combination of a weak acid with the salt of the weak acid or a weak base with the salt of the weak base is called a buffer solution. And the thing about the buffer solution is that it has this unique ability to resist changes in pH if you add a small amount of either acid or base to it, right? That makes the buffer solution very unique, because almost all other solutions, if you add a small amount of acid or a small amount of base to it, the pH will change widely. But in the case of a buffer solution, the pH will change, but only to a very small extent, all right? So let's look at an example. Let's say you have a mixture of acetic acid and sodium acetate, all right? That would be a buffer solution, right? If you add a strong acid, and this is where you're going to see how the buffer works, right? If you add a strong acid to the buffer, the acid will produce H+ ions in the aqueous solution, and the H+ ions will react with the acetate, which is the conjugate base portion of the buffer. So the result would be the formation of a weaker acid, right? So basically what you're doing is converting in this reaction a strong acid to a weaker acid. The weaker acid will not have a profound effect on the pH. So therefore, even though the pH will fall a bit, it will not fall to a large extent, all right? If you add a strong base to a buffer solution, this is the reaction that will take place. The base will create hydroxide ions in the aqueous solution, and the hydroxide ion will react with the acid part of the buffer to form the acetate ion. The acetate ion is a much weaker base compared to the hydroxide ion, and therefore the acetate ion will not have a profound effect on the pH. Again, the pH will change. In this case, the pH will rise, but it will not rise to a very large extent, all right? So that's basically, in a nutshell, how a buffer works. Okay, and then finally, before we go back to the assignment questions, I want to show you this particular graph because it demonstrates how a buffer works when you add a small amount of acid to it compared to water. Excuse me, let me get some water here. Okay, sorry about that. So, what is being shown here is the changes in pH as you add incrementally acid to it. In this case, hydrochloric acid. And you'll notice that in the case of water, pure water has a pH of 7. And as you add acid to it, as the amount of acid increases, the pH falls dramatically. And then it kind of level off later on. So that's basically how water behaves. But look at what happens when you do the same thing to a buffer. The pH does change, but very slightly, all right? So the pH will decrease, but not as dramatically as in the case of water. Okay, so that's basically how that, how buffer works and how buffer behaves, all right? So let's see if we can answer these questions. And then after answering these questions, we're going to go into the assignment questions, which we had to skip over. So this question says, which of the following are buffer systems? Now remember, by definition, a buffer is a mixture of either a weak acid and the conjugate base of that acid, or a weak base and a conjugate acid of that base, all right? So for the first one, they gave you potassium fluoride and hydrofluoric acid in a mixture. So would you consider that to be a buffer? Potassium fluoride and hydrofluoric acid. Anybody? Okay, let me give you a hint. In order to answer questions like these, you have to be able to identify a weak acid and or a weak base, right? So in this case, we have an acid, which is hydrofluoric acid. And I told you guys that there are 6 acids that you need to memorize as being strong acids. Can anybody tell me what those 6 acids are?
HCl, HBr, HI, HNO3, HClO4, H2SO4.
Very good. All right. And based on what you just said, hydrofluoric acid would not be a strong acid, right?
Correct.
Good. So I ask the question again. Is that mixture of potassium fluoride and hydrofluoric acid, is that a mixture of is that a buffer mixture?
Yes,
Or-
because it has the salt and it's a weak acid.
Exactly. So the answer for A is that because the potassium, this is a typo, this should be hydrofluoric acid. So please make a note of this, right? So because the hydrofluoric acid is a weak acid and you have the fluoride ions from the potassium fluoride, that solution will be a buffer solution. Okay, very good. What about B? Is B a buffer solution or buffer solution?
No, because it has a strong acid.
Exactly. The hydrobromic acid is a strong acid, so therefore that solution is not a buffer solution. Okay, and then for C, let me explain that because even though it might be a bit challenging being introduced to this for the first time, in the case of C, the sodium carbonate here has a carbonate ion, and the sodium bicarbonate here as a bicarbonate ion. So what you're actually comparing is the carbonate to the bicarbonate, right? And the bicarbonate is a weak base, and the carbonate would be the conjugate base. I'm sorry, the bicarbonate would be a weak acid, and the carbonate would be the conjugate base of that weak acid. So therefore, as a result, the answer is that this is a buffer solution. And you could also look at it in the other way as shown here in this sentence. You could look at it in terms of the carbonate ion being weak, being a weak base, and the bicarbonate would be the conjugate acid of that base. The result will still be the same, all right? Okay, so with that out of the way.
Question.
Yes, ma'am.
How do you recognize the salt again?
A salt is basically a combination of a cation, usually metal, like potassium, sodium, copper, whatever, and the conjugate base of an acid like fluoride, nitrate, sulfate, bisulfate, and so on.
Okay, thank you.
Okay, let me see here. Okay, you know what? I'm trying to decide what to do. Okay, let me move on to the next page. And then because the next page gives an example of a buffer solution type problem. It says, calculate the pH of a 0.30 m ammonia combined with a 0.36 m ammonium chloride buffer system. And then the question says, what is the pH after the addition of 20 mils of 0.050 m sodium hydroxide to 80 mils of the buffer solution? So the first thing I would write down is you don't even need this, to be perfectly honest, but it doesn't hurt. So this is the equation which shows you how the ammonium is converted to the ammonia, all right? What you really need is this equation right here, which is the Henderson-Hasselbalch equation for this system, all right? You need to find out what the pKa is, and that can be a bit of a challenge because pKa's are not given for the ammonium ion. But there's one thing you need to remember, and let me see if I can write this down here, and that is that pKa for a weak acid plus pKb for the conjugate base is equal to 14.00. How could I forget? All right. So this is what you're going to need in order to get the pKa that would be here, right? So you'd have to go to the tables. You have to look up the Kb for ammonia. And if I remember correctly, Kb for ammonia is 1.8 times 10 to the minus 5, which means that pKb is equal to the minus log of that. Let me see what that gives. So 1.8 times 10 to the minus 5 minus log of that gives you 4.74. So let me write that down here, 4.74. And therefore, pKa would be equal to 14.00 minus 4.74. And that would be equal to 9.26, according to my calculations, which I'm very confident that it is because that's a value that's right here, all right? So the pKa value, you'd have to calculate it, okay? And then you plug that, go back to my, you plug this value where the pKa is, and you plug in the values for the concentration of ammonia, which is 0.30, and ammonium, which is 0.36, and you're going to end up with this equation right here. And then you do your calculation, and the pH of the solution is going to be equal to 9.17. All right. So that's basically how you calculate the pH of such a solution. Now, the question also asks, what is the pH after the addition of 20.0 mils of 0.050 m sodium hydroxide to 80 mils of the buffer solution? So please note the pH of the solution before you add anything to it. Now, what happens when the sodium hydroxide is added to the buffer? Well, sodium hydroxide is a base, so it's going to react with the acidic part of the buffer. In other words, the sodium hydroxide is going to react with NH4 plus to get water and ammonia. Initially, these are the values. Now, well, let me back up a bit here. Now you might be wondering, how do we get the moles of ammonium, and the moles of hydroxide? Well, it's very simple actually, because they gave you the volume of each solution and you know the molarity of each of these two. In the case of the ammonium, that would be equal to the molarity, which is 0.36, times the volume, which is 80 mils, all right? I want to see if I can squeeze that somewhere here. Let me erase all ink and let me do this. So the moles, okay, what's going on here? Okay, so, okay, what's going on? Where is, okay, my pen is acting up now for some strange reason. Okay, let me do this up here. So moles of ammonium, I'm sorry, will be equal to the molarity, which is 0.36 moles per liter, multiplied by the volume, which is 80.0 mils, which you have to convert to liters, which is 1 liter over 1,000 mils. All right. And when you work that out, that will give you this value right here. All right. And then similarly, let me see if I can squeeze it over here. Moles of NaOH will be equal to the molarity, which is 0.050 moles per liter, multiplied by the volume, which is 20.0 mils. And then we multiply that by 1 liter over 1,000 mils. And when you work that out, you're going to get the value right here, all right? So those would be the initial moles of both the ammonium and the hydroxide. And then we look at what happens at the end of the reaction, because again, this is an acid-base reaction. It goes in one direction. So basically the limiting reactant will be used up. Oh, by the way, I forgot to mention also that we get this value here, which is the moles of ammonia, by doing something similar to what we did here. So let me just show you quickly how that is done. That would be 0.30 moles per liter multiplied by the volume, which again is 80.0 mils, which you have to convert to liters, 1 liter over 1,000 mils. And that gives you this value right here, all right? Okay, so as I was saying, that's a start, and then the limiting reactant, which is the hydroxide ion, will be used up. So basically at the end of the reaction, all of this will be used up. 0.001 moles of that would be used up. This would be the amount remaining. And as far as the ammonia is concerned, the amount added to that would be 0.001. So this becomes 0.025. And then now what we need to do is find the final volume of the solution. You're mixing 80 mils with 20 mils. That gives you 100 mils. And then you find the molarity based on that for each of the components remaining in the solution after the reaction ends. So that would be the ammonium and the ammonia. So basically you're going to divide the concentration of ammonia by the volume in liters. This is 100 mils. That becomes 0.10 liter down here. And that gives you the molarity of the ammonium. And you do a similar calculation for the ammonia. And then you plug those values into this equation here. Of course, the pKa still will be equal to 9.25. And then you're going to get your pH of that solution, which is 9.20. And if you compare the two pH values, the one after adding the sodium hydroxide and the one before you add the sodium hydroxide, you'll notice that there's not much of a difference. The difference between those two values would be 0.03, right? And that basically demonstrates how a buffer works, all right? And let me just say that buffers are very important, especially when it comes to biological systems. Certain processes, certain biological processes has to take place. Well, let me start off by saying certain biological processes more than likely will be chemical processes. And a lot of these processes require that the pH of the medium that they're in is within a certain range. And therefore, buffers play a very important point in terms of maintaining the pH environment so that we can have these processes occur. All right. So that's, if not any other reason, that's a very important reason for us to study buffers and understand how they work. Okay. So now that I've gotten that out of the way, now we can go back to the assignment. So let me keep this and let me go to, okay, where is it? Let me go here and let me go to the assignment. Okay, so the question that we got stuck on. Oh, by the way, did I? Okay, so this is the question. This is how far we got before I realized that we didn't cover buffers. So basically, this question here is dealing with a buffer solution, right? So what we have so far is the amount of ammonia and the amount of the ammonium, all right? So what we can do now is calculate the concentrations of each. So the concentration of, well, first we need the total volume. Let's do that first. So the total volume will be equal to the 40 mils that we mix with the 20 mils, all right? So that would be 40.0 mils plus 20.0 mils, and that is equal to 60.0 mils, all right? So we can now calculate the molarity of the ammonia, which is equal to 4.00 times 10 to the minus 3 moles divided by 60.0 mils, which we have to convert to liters. So 1 liter over 1,000 mils. And in this particular case, the answer I got is, hold on 1 minute. Oh, okay, let me do this here. So that's 4 times 10 to the minus 3 divided by 60, 1,000. Okay, so the answer I got for this part here is 0.0667 M. And then I'm going to do the same thing for the concentration of ammonium. And that will be equal to the same, actually. So let me just put this here, concentration of ammonium, because it's the same numbers. All right, so let me erase this here. Okay, so what is the pH? Well, the Henderson-Hasselbalch equation is what we'll be using here. And that equation is pH, in this case, will be equal to pKa plus log the concentration of the base, which is NH3, divided by the concentration of NH4 plus. But since the concentration of NH4 plus is equal to the concentration of NH3, that means that these two will cancel out. So you're going to end up with log of 1 here. And can anybody tell me what log of 1 is? What is log of 1 equal to? Come on, you guys should know this from your algebra.
0.
Exactly. Log of 1 will be 0. So therefore, what that tells us is that the pH is going to be equal to the pKa, right? So all we have to do now is find the pKa of ammonium, which we did before from a previous example. The pKa of ammonium is 9.25. All right. And that's basically how we do that. And this kind of buffer, we call this an ideal buffer, right? An ideal buffer is where the concentrations of the base and the acid are equal to each other. So therefore the pH becomes equal to the pKa, all right? So that's basically how that is done. Okay, any questions about this one? Any questions? Any questions? Any questions? Okay, so let me go back to the assignment and scroll down. Okay, now in this case, you're mixing the solution with 20 mils of ammonium chloride, all right? Now, in this case, what we're doing is mixing directly the base with the conjugate acid of the base, right? So let me hear what ideas you guys have in terms of at least starting to solve this problem. How would you solve this problem? Now remember, the original solution of ammonia was 0.100 m and the volume is 40 mils, right? And then you're mixing it with 20 mils of the 0.200 m ammonium chloride solution. So let me hear your ideas about this. How would you solve this problem? Or how would you start solving this problem?
You would make an equation.
Okay. I wouldn't start there, but okay, let me see if I think I should have enough space to do this. Let's see here. Okay, so what would be the equation?
NH3 plus NH4Cl.
Nope.
Oh.
Or better yet, let me not use H though. Not that it's wrong. Okay, so the reaction would be NH4 plus. Why did I do that? NH4 plus to form NH3 plus H plus. That's the equation, all right? But the equation is not really necessary because you can use the Henderson-Hasselbalch equation, which is pH is equal to pKa plus log of the concentration of NH3 divided by the concentration of NH4 plus. That's how you're going to find the pH. So what you really need to do is find these terms here and here. So how would you find the concentration of ammonia after mixing? Remember, you start off with 40 mils of the 0.100 m ammonia solution, and then you're adding 20 mils of another solution. So basically, you're diluting. You're diluting the ammonia solution.
Would it be the 0.1 molarity times 40 is equal to M2 times 60.
Exactly. So in this case, you divide by 60.0 mils here, because this would be your M2, all right? And when I did that, I got 0.0667 M. Okay, what about the ammonium? How would you calculate the molarity of the ammonium after mixing?
You would do something similar with 20 times 0.2.
20.0 mils times 0.200 M divided by
60.
60.0 mils, exactly. And according to my calculation, this gives, guess what? 0.0667 M as well. So that means that the concentration of ammonia is equal to the concentration of ammonium. So what does that mean?
pH is equal to kPa.
pKa, which is equal to what we saw before, which is what? 9.25. And that's it. Or 9.26. Is it 9.26 or 9.25? Whichever it is, I don't remember exactly. From the previous problem, I think it was 9.25. So I'll stick to that. All right. Any questions about this? Any questions? Okay, so that basically represents the end of assignment number, what is it? Assignment number 4, yes. So again, I expect this to be completed by hand and submitted to yours truly via Canvas. Make sure that it's written up neatly, make sure that it's submitted as a PDF document. Make sure that you write your name at the very top of each page. And what else? Oh, and not all of you were guilty of this, but a couple of you did not write or complete the assignment on the original document. So please, please make sure that you complete this assignment on the original document that is posted in Canvas, all right? I'm going to make the deadline date for submission of this assignment be Wednesday, all right? So I'm going to create a Dropbox and that would be available for you to submit your assignment that way. All right. So, yes, sir.
On the original assignment.
Well, you know, at least 2 persons from the class, they basically completed the assignment on, like, you know, some ordinary sheet of paper, and they submitted it that way. But I do want it to be on the original document. You know, so what you could do is print it and write your answers on it. Or if you have the, what do you call it? I forgot the term. If you can write on the document, on the computer itself, that's fine by me. And you submit it as well, all right? But yeah, not on a separate sheet of paper, please, all right?
Okay.
Okay, so.
I have a question.
Yes, ma'am.
Regarding the test for this week, it's going to be on assignment 3 and 4, correct?
Well, firstly, let me just check something here, because if I'm not mistaken, the test will be next week. Hold on, let me check the syllabus here.
The syllabus said the week of the 17th.
Hold on. Oh, shoot, the syllabus is, oh, right. I discovered that the syllabus was not, hold on, the syllabus was not, was deleted somehow from the files. And I don't know how that happened, but let me, let me just say that I think what you're referring to is the syllabus that you see on the announcement page, right?
Correct. Yes, sir.
Yeah, I made changes to that and I forgot to make changes, the corresponding changes on that particular announcement. So I'm going to see if I can find it.
So are we
Uh,
moving the test to next week then?
Yeah, but I want to make sure I have that in the syllabus. So let me check it out. Let me. Yeah, there was a whole lot of errors on the original syllabus, so I made some changes, including the office hours. So yes, the test will be next week, the week of the 24th. And while I'm at it, let me upload the new syllabus. Hold on.
Okay, and in regards to that test, are you going to do another answer key that we're able to use to study?
You mean a past test, answer key?
Yes, sir.
Yeah, that's a plan.
Okay, thank you.
Yeah, let me do this. Let me upload this before I forget. Knowing me, I tend to forget stuff sometimes. Okay, so if you go to files and then syllabus, there's a folder labeled syllabus. That's where I have posted the revised syllabus. And I'm going to try to remember to change the stuff on the announcement page. I'm going to see if I can do it today. But yes, the test will be next week. So again, the same arrangement as last time. Basically, you're just going to register or sign up on the website for the testing center, make an appointment for a date and do the same thing as before. Everything will be provided for you then. Okay, so what I'm going to do now, and you know what? Let's take a break. It's now 11:47, so let's get back together at 12, and then we'll go from there. All right. Okay, so let's get started or restarted. All right, now before we look at this diagram here, I want to, hold on 1 minute, 1 minute, 1 minute. Okay, so let me get out of this here. Okay, why is this thing not behaving itself? Okay, and let me get to oh, by the way, I've just created a Dropbox for assignment number 4, so make sure that you submit your assignment in that Dropbox. Okay, what am I trying to get to? I'm trying to get to assignment number 5. Okay. So let me bring assignment number 5 up if I can find it. Assignment number 5, and let me publish it now so that you guys can have access to it. Okay, so there's a question here. The first question I want us to look at, and I think we covered this in the previous chapter. It says calculate the pH of a 0.25 m sodium formate solution given the value of Ka for formic acid is 1.8 times 10 to the minus 4. So I'm going to need some space for this. So again, I'm going to go to my writing pad here, and I'm going to get rid of this here. And let me just write down the essential information. So the concentration of sodium formate, I'm going to use NaA again for that purpose. That will be equal to 0.25 m. And the Ka value for the formic acid is equal to 1.8 times 10 to the minus 4, all right? So we know that when sodium formate is added to water, it dissociates to form Na plus A minus. And then the A minus itself, being a conjugate base, will react with water to form HA and OH minus. All right. So we can construct an ice table. And let me just say before I do that, by virtue of the fact that hydroxide is being formed, that tells us something. It tells us that the pH will be greater than 7. All right. So initially, the concentration of the A minus would be the 0.25 here. And this would be 0, and that would be 0. And the change here would be minus X. This would be plus X. That would be plus X. So at equilibrium, you're going to have 0.25, whoops, minus X. Here you're going to have X. Here you're going to have X. And then we can write down the Kb expression. Kb is equal to the concentration of HA times the concentration of OH minus divided by the concentration of A minus. So all we have to do now is plug in the terms, and you're going to end up with X squared over 0.25 minus X, and that would be equal to Kb. Now the thing is, we don't have Kb for the base, but we have Kb for the acid. So remember now, Ka times Kb is equal to 1.0 times 10 to the minus 14. So to find Kb, that would be equal to Kw divided by Ka, which is 1.0 times 10 to the minus 14 divided by the Ka, which is 1.8 times 10 to the minus 4. So this would be equal to 1 times 10 to the minus 14 divided by 1.8 times 10 to the minus 4. So according to my calculations, this works out to be equal to 3.7 Oh, something is wrong here. Hold on. 1 times 10 to the minus 14 divided by 1.8 times 10 to the minus 4. Okay, I knew something was wrong. Okay, so the value I got for KB in this case is 5.6 times 10 to the minus 10, 10 to the minus 11. Let me check this again. Okay, so this is the KB value, which is equal to this here. Again, we assume that X is much less than 0.25, which means that 0.25 minus X is approximately equal to 0.25. So that will simplify this equation to get X squared over 0.25 is equal to 5.6 times 10 to the minus 11. So that means that X will be equal to the square root of 0.25 times 5.6 times 10 to the minus 11. So let's see here, 5.6 times 10 to the minus 11 multiplied by 0.25. And then I find the square root of that. And the value I got for X in this case is 3.7 times 10 to the minus 6. And we can go on to find the percent dissociation, which would be equal to 3.7 times 10 to the minus 6 m divided by the initial concentration, which is 0.25 m. And I'm quite sure this would be less than 100%, I mean less than 5%. So 3.7 times 10 to the minus 6 divided by 0.25 times 100. And the answer I got is 1.5, I'm sorry, times 10 to the minus 3%. So therefore, we can say that X is equal to 3.7 times 10 to the minus 6, which would be equal to the concentration of OH minus. So you all know what we're going to do next, right? What's the next step? Since we know the concentration of OH minus, what's the next step?
POH.
Okay, so we find, let me do that up here. So we find the POH, which is equal to minus log of 3.7 times 10 to the minus 6. And according to my calculation, that works out to be equal to 5.43. And therefore, we find the pH, which is equal to 14.00 minus 5.43. And let's see what that gives. That gives 8.57. So 8.57. And that would be the answer to the question. All right. Okay, any questions about this particular problem? Any questions? Okay, so let me go back to the PowerPoint. And let's talk about some applications of what we just discussed. So we talked about buffers. So just to remind you what a buffer does, a buffer basically resists changes in pH when a small amount of acid or base is added to it. And one can see an example in biological systems of the importance of buffers right here. I'm sorry, I keep doing that. So what is being demonstrated here is the red blood cell, all right, also known as erythrocyte. And basically, you know, or you should know from your biology courses, the role of the red blood cell. It basically transports oxygen from the lungs to other tissues that may need it to, you know, produce energy. Well, to use energy to carry out its function, whatever the tissue function is. And also it's used to transport carbon dioxide away from it, all right? So what is being shown here are the different steps involved in these processes. This represents the red blood cell that is delivering oxygen to the tissues, right? So the equilibrium, which is responsible for the buffer action in this particular case, is the reaction where carbonic acid dissociates to form the bicarbonate, right? So this is the weak acid, and this is the conjugate base of the acid, right? So what happens when the carbon dioxide enters the red blood cells? It reacts with water, and that forms the carbonic acid. Then you have the equilibrium between the carbonic acid and the carbonate ion, which produces the hydrogen ion, which itself will react with this oxygenated hemoglobin anion right here to form this here, which is basically the same thing with the hydrogen ion added to it. And then that would result in the release of oxygen, which will be delivered to the tissues, right? So that's basically what happens when oxygen is delivered to the tissues, and the red blood cell is also taking away carbon dioxide from the tissues. Now, what is being shown here is what happens in the lungs, right? Where carbon dioxide is basically released to the lung, while oxygen is being taken from the lung into the red blood cell. And it's basically the reverse of all the steps that we described right here, right? So the oxygen will attach itself to the hemoglobin molecule, then this reaction takes place, then this reaction takes place. You have an equilibrium between the carbonic acid and the bicarbonate, and the bicarbonate ion, and then the release of carbon dioxide to the lungs, all right? So that's just basically what is happening. And in all of this that's happening, the pH of the blood is being maintained as a result of the buffer action of the two important components of the buffer, which would be the bicarbonate and the carbonic acid. Okay, so let's move on now to talking about titrations. Now, this is something that you may or may not have done before in your General Chemistry 1 class, but basically what titration is all about, it's a type of what we call volumetric analysis, where you basically use a solution of known concentration to determine the concentration of another solution based on the reactions between the solutes in those two solutions, right? So basically what you do is that you add one solution to another until the amount of solution added is of the right stoichiometric amount in terms of its equivalence to the amount of this other solute present in the solution that is being added to. And then you get some data, and as a result of the data, you can determine a couple of things. You could determine the concentration of one of the two solutions based on the concentration of the other solution. Some terms you need to define here: the equivalence point, the point at which a reaction is complete. Another way of looking at this, it is the point where the amount of one substance being added to the other, they're both stoichiometrically equivalent at that point, all right? So that's called the equivalence point. Now, in order for you to determine the equivalence point, you need to have some way of showing that the reaction has reached that particular point. Now, in the case of acid-base titration that we're going to discuss, we typically use a substance which is known as an indicator. And an indicator is basically a dye which takes on the color of, it takes on a particular color depending on the acidity or basicity of the solution it's in, right? So the choice of an indicator is very important, as you're going to see shortly, to indicate the equivalence point, all right? So just to briefly describe the practical aspects of titration, if you have not done this before, what you're looking at here on your screen are the basic items that you're going to need in order to carry out this titration process. So you're going to need an Erlenmeyer flask. This is also known as a conical flask. You're going to need your indicator, which is in this bottle right here. And in your flask will be one of two solutions that you'll be analyzing, right? Now, for the experiment that I typically do in the lab, we typically have the acid inside the Erlenmeyer flask right here. And then we have this piece of glassware known as a burette. Now, this is partially shown. What I'm going to do is see if I can find a picture of one online so that you see what it looks like. But just to briefly describe what the burette is, it's basically a long cylindrical piece of glassware. Let me do this here. So burettes. Okay, so let me see if I can get a full picture of one of them. So you can see, no, that's not it. Okay, let me see here. Let me see. Oh man, okay. Images. Okay, let me show you this here. Okay, so this is, I wonder if I can get a close-up. Okay, so this is the mirror, this long cylindrical piece of glassware right here. That's a burette, right? And if you look at it closely, you'll see that the way it's graduated, it starts at 0 at the top, and then it goes down and increases until it gets to a value down here. Now, this burette here is a 50 mil burette. So basically, the last value that is at the bottom of the burette is 50, right? So that's basically how it's graduated. You'll notice also that there is a what we call a stopcock, which is basically a tap, which allows for the flow of the liquid through the tip, which is right here. All right, so that's a burette, and typically what we do is that we add your solution, whatever the solution that you're going to place in it, you pour it in the top part here. Of course, because of the narrow radius of the top part, it's advisable that you use a funnel to pour your liquid into it, and then make sure that this is closed. And the cross position, as you can see here, represents the closed position. And then you pour your liquid into it until the meniscus, I should say, gets above the mark here. And then you'll basically eject some of the liquid through the tip. Of course, you should have something here to collect the liquid. And then you read off your first reading based on the scale that is etched on the stem of this piece of glassware. All right. So that's a burette, and that's basically what is shown going back to the PowerPoint here. Basically, that is what is being shown here. This is just the bottom part of the burette. All right. So in the experiment that we conduct in my labs, basically, as I said before, you're going to have your acid solution here, and the base solution would be in your burette. All right. You have to record the volume reading on your burette initially. And also, very important, you need to determine the volume of the acid that will be placed in the flask right here. And typically we use what is known as a pipette, which I won't describe right now, but the pipette is basically a piece of glassware which allows you to measure accurately a particular volume. So you can have a 10 mil pipette, 25 mil pipette, and so on. So we would measure a certain amount of the acid in here. And then what you'll do before you add your base to it, you would add at the most, or I should say at least 2 drops of your indicator to your solution. Now, as I said before, the indicator takes on a particular color depending on the acidity or basicity of the solution that you add it to. The indicator that we use in our experiments is known as phenolphthalein. And that indicator is colorless in acid, but pink in base. So when you add 2 drops of the indicator to this solution here, it is going to remain colorless. And then you start adding your sodium hydroxide into the flask, and what will happen is that the color changes to the pink color, which indicates that you have now added enough base to react with all the acid that is present in the flask. Once you do that, you record your second reading, and then you're going to do some subsequent calculations to determine whatever you need to determine or whatever the aim of the exercise is. Usually, it's to determine the concentration of one based on the concentration of the other, right? So that's basically, in a nutshell. I mean, there are more details involved, but I don't want to get into all of that. But basically, that's what's involved in acid-base titration. And let me just say that acid-base titration is not the only type. You have different types of titration. You have redox titration, precipitation titration, and others, right? But for our discussion, for our purposes, we'll be limited to acid-base titration, all right? Okay, so let's talk about pH changes as a titration occurs. So what I'm showing you here on the screen is a plot of pH on the y-axis versus the volume of sodium hydroxide being added to your acid solution. So if you imagine the setup that I just showed you, the sodium hydroxide will be delivered from the burette, and that's where you're going to get the readings here so that you can make a plot. Now, as far as the pH is concerned, what you can do is use a pH meter. And I think I showed you a picture of one from the previous chapter, all right? So if you need to refer to that, you can look at that to see what it looks like. So basically, as you're titrating your acid-base solution, or as you're doing your acid-base titration, you're continually measuring the pH, and you're going to get your data, as you can see here to the right, and then you do your plot, pH versus the volume of sodium hydroxide. And as you can see, it takes on a kind of S-shaped curve, right? Where at the inflection point right here, that would be the equivalence point. That would be the point where the amount of sodium hydroxide added is stoichiometrically equivalent to the amount of acid that is present in the Erlenmeyer flask. So, as you can see here, before you add any sodium hydroxide, the pH of the acid solution is 1. So what that indicates to me is that the molarity of the sodium hydroxide, or I should say the molarity of the hydrochloric acid, is 0.10. And then as you add sodium hydroxide to it, what happens is that some of the sodium hydroxide will be reacting with the acid, but there'll still be acid left over as a result. So as a result of that, the pH still remains below 7. But the pH continue to gradually increase as you add more and more base, until when you get close to the equivalence point, the pH makes a sudden jump through the equivalence point until you get to this point right here, which indicates that now you're past the equivalence point and the solution is basic. And as you continue to add more and more sodium hydroxide, as you can see, the solution becomes more and more basic, which means that the pH becomes higher and higher. It increases as you add more sodium hydroxide. And that's basically what is involved when you're doing your titration. There's a increase in the pH, but it's gradual initially, and then you get to the equivalence point, and then the pH increases after that continually. All right, now this plot here is a plot of the titration of a strong acid and a strong base. And more specifically, I think this is, in fact, I'm correct, the reaction between the strong base, which is sodium hydroxide, and the strong acid, which is hydrochloric acid, right? And I would go on further to say that the molarities of each of these would be, in the case of sodium hydroxide, the molarity of the sodium hydroxide is 0.100 m, and the same would be true for the volume of the hydrochloric acid, which is 0.100 m, all right? So that's basically what is involved in the titration of a strong acid versus a strong base. Okay, so, this is just showing you the net ionic equation, all right? Hydroxide plus H plus gives you H2O. Okay, now in the case of the titration of a strong acid, a weak acid versus a strong base, the shape of the pH curve is a bit different. And let me explain what I mean by that. So if you were to compare this one to the one that I showed you before, you'll notice that initially the pH starts at a higher value compared to the previous graph, right? And the reason why is because in the case of this plot, the acid is weaker, right? And therefore, the pH would be higher as a result, right? So the acetic acid is weaker than the hydrochloric acid, and therefore the pH would start at a higher value, which from the look of things here, I would estimate this to be about 3, all right? So the pH starts off at 3, and then as you add your base, it continues to increase until you get to the inflection point again, which is the equivalence point. And then when you add more base, it continues to increase. Now, the thing about the equivalence point in this case is that unlike in the case of the titration of the strong acid and strong base, where the pH at the equivalence point is 7, in this case, the pH of the equivalence point will be greater than 7, all right? And there's a reason for that, which we will get into shortly. But basically, at the equivalence point, the solution will be basic, right? And one rule that you can follow to make a prediction as to whether or not the equivalence point will be below, above, or at 7 is comparing the strength of the acid to the base. If the base is stronger than the acid, then the pH would be above 7, because at that point, the solution will be basic. Now, if you were titrating a strong base, or I should say a strong acid versus a weak base, then the pH will be below 7, all right? But in this particular case, it's a weak acid, strong base titration. So at the equivalence point, the pH would be above 7. In other words, at that equivalence point, the solution would be basic, all right? So that's basically what happens in the case of a weak acid, strong base titration. So as I said before, the pH would be above 7 at the equivalence point. Okay, oh, and actually here it shows you the reason why. If you look at this here, you'll see that the acetate ion, which is formed at the equivalence point, will be hydrolyzed by the water, right? The result would be the formation of hydroxide ions, which makes the solution basic. So that is the reason why the pH will be above 7 at the equivalence point when you titrate a weak acid versus a strong base. Okay. Any questions about the titration curves for a weak acid, strong base, or for a strong acid, strong base for that matter? Any questions? Any questions? Okay, so let's look at what happens in the case of a strong acid, weak base. Now, I must admit, I don't like this curve because they did the opposite here. What they're doing is adding acid to the base, which is already in the Erlenmeyer flask. But in any case, we can still work with this. So we're talking about a strong acid, weak base. The strong acid is hydrochloric acid. The weak base is ammonia. And as you continue to add your acid to the base, which is already in the solution, you're going to start off with a relatively high pH. That's a base before you add anything. And then when you add your acid, the pH falls until you get to the equivalence point. And then as you add more acid, the pH falls again and continue to decrease. And you'll notice here at the equivalence point, the pH is less than 7, right? That's what happens when you titrate a strong acid versus a weak base. At the equivalence point, the solution, the resulting solution, will be acidic, all right? And the reason why that happens is because at the equivalence point, the ammonium ion which is formed will react with water to form ammonia and, more importantly, hydrogen ions. And this is the reason why the pH of the solution at the equivalence point will be below 7. Okay, so much for that. So let's look at this problem here. And this is a typical titration type problem. It says exactly 100 mils of a 0.10 m nitrous acid solution is titrated with a 0.10 m sodium hydroxide solution. What is the pH at the equivalence point? Well, before doing any calculations, I can tell that at the equivalence point, the pH would be greater than 7. And the reason why I can tell that is that we're talking about titrating a weak acid, which is nitrous acid, versus a strong base, which is sodium hydroxide. All right, so whatever the answer that we should get, it should be greater than 7, all right? Okay, so the first thing I would do is write down the equation for the reaction between the nitrous acid and the sodium hydroxide, which provides the hydroxide ion. So this would be the balanced equation. It's an acid-base reaction, so it's not reversible. The reaction will go in one direction. So the initial number of moles that we're going to have here is for the nitrous acid, that would be 0.01. Now, the reason why is because the volume of nitrous acid is 100 mils, and you are basically determining the number of moles by multiplying this volume in liters by 0.10, and that's how you get this, right? As far as the hydroxide ion is concerned, the number of moles of the hydroxide ion will be the same because we're talking about the equivalence point. And then you'd have, at the end of the reaction, all of this will be used up, all of this will be used up, and the number of moles of the nitrite ion will be 0.01. So basically what we need to do now is find the concentration of the nitrite ion, which means that we need a final volume, and the final volume will be 200 mils. Now we know that because the molarities are the same. And therefore, if 100 mils neutralizes, if 100 mils of nitrous acid neutralizes the sodium hydroxide exactly, then the volume of the sodium hydroxide must be 100 mils, because after all, they have the same concentration. So the total volume, when you mix both of them together, would be 200 mils. So we now have what we need to calculate the molarity. We simply take the moles divided by the volume in liters, and that gives you the molarity. And then what we have to do now is look at the reaction that the nitrite ion will have with water to form the hydroxide ion and nitrous acid. So in other words, we have to set up an ice table for that. Initially, the concentration of the nitrite would be the 0.05. We don't need to worry about the water. This would be 0 and this would be 0. And then we do the same things like we did before. We look at the changes. Then we write down the equilibrium expressions. And then we plug them into the Kb expression for the nitrite ion. And then we do the simplifying assumption to solve for X. And then that would give us the concentration of hydroxide. The Kb, by the way, that would be equal to, let me write this down here. You won't get that directly from the tables. That would be equal to, okay, what's going on here? That would be equal to Kw divided by Ka. So you'd have to look up the Ka value, put that here, divide by the Kw, which is 1.00 times 10 to the minus 14, and divide by whatever the Ka is, and that will give you the Kb, which is this right here. So once you solve for the hydroxide ion concentration, then of course you all know what to do to get the pH. Basically, you find the pOH. Whoops. Okay, let me erase this thing so that you can see what's happening here. All right, so once you find the pOH, then you can find the pH, which is 14 minus 5.98. And that gives you the pH, which is 8.02. And just as we predicted, the pH is actually greater than 7. In this case, it's 8.02. All right. Okay, any questions about this particular example? Any questions? Any questions? Okay, let's see what's up next. Let's see here. Okay, so before, should I do this? Okay, let me talk about acid-base indicators in a bit more detail. Okay, so as I mentioned before, acid-base indicators are basically dyes which takes on a particular color based on the acidic or basic environment it's in, all right? So we can, in fact, I would say that indicators are basically weak acids and weak bases. So we can use a general formula for representing a weak, not a weak acid, but an indicator, which is a weak acid in this particular hypothetical example. So when that dissociates, it forms H plus and Ion minus. Now, the thing about these molecules is that they are typically colored, right? So you might have one that is, let's say, blue, and another one that is, let's say, yellow, all right? So basically, in this particular case, if you have more of the blue molecules than the yellow molecules, then the blue molecule, then the solution will be blue, basically. All right, and vice versa. Okay, now, as a guideline, this is what you'll actually observe. If the ratio of the undissociated molecule to its conjugate base is greater than or equal to 10, the color of the undissociated molecule will predominate, all right? On the other hand, if the color of the acid molecule, or I should say, if the ratio of the acid molecule to the conjugate base is less than or equal to 10, then the color of the solution would be based on the color of the conjugate base, right? So what you see down here are some indicators and their colors respectively in acid or base. And to the extreme right, you see the pH range within which the color change will occur, all right? That's very important because in order for the indicator to indicate the equivalence point in an acid-base titration, the pH at the equivalence point should fall within the color change pH range indicated for each of these indicators. All right. And we can see that application. Let me just skip this right here and move on to the pH curve right here. So this is the titration curve for a strong acid with a strong base. All right. And as you can see here, the jump in the pH goes from a low of about 3 to a high of about 12. So the indicator that you choose in order to show where the equivalence point is must have a pH range in terms of the color change that falls within that jump right there, right? So what you see here are 3 indicators that are along with their color change pH range. And as you can see clearly, the 2 that will change your color within that pH jump right there will be the methyl red, which will go from red to orange, and the phenolphthalein, which will go from colorless to pink, right? So in order for us to determine the equivalence point in the titration of a strong acid versus a strong base, you would choose either phenolphthalein or methyl red to observe that equivalence point. You would not choose thymol blue because, as you can see here, the color change for thymol blue will occur before the equivalence point. So basically, if you were to do the titration, you're going to see a color change, but that color change will not indicate that you'd have reached the equivalence point in this particular titration. Okay, let's see what's next. So here's a question, which is based on what we just discussed. It says, which indicators would you use, well, it says indicator or indicators, would you use for the titration of nitrous acid with potassium hydroxide? You're talking about a weak acid titrating or titrated with a strong base. So basically, you have to ask yourself the question, will the pH at the equivalence point be greater or less than or equal to 7? So let me hear what you guys think. Will the pH at the equivalence point be less than 7 or greater than 7?
Greater than.
Greater than. And the reason why is because you're talking about titrating a weak acid with a strong base, right? So basically, we know that the pH will be greater than 7. So based on that fact, based on the fact that the equivalence point for this titration is greater than 7, which of these indicators would you choose to indicate the equivalence point in this type of titration?
Maybe phenylephthalin and cresol red.
Yeah, cresol red and phenolphthalein. Yes, I can appreciate you might have some difficulty pronouncing that, but we call it phenolphthalein.
Okay.
And I'm very thankful very often that we're not tested, or when I was a student, I wasn't tested on pronunciation of words and also spelling in terms of chemistry. But yes, so the answer is, you're correct. The answer is either cresol red or phenolphthalein would be the indicators of choice in order to indicate the equivalence point of a titration of a weak acid versus a strong base. All right. Okay. So now that we have covered all this, we can get started, or not get started, but continue to look at, hold on. the assignment questions. So let me go back to this right here and go to assignment 5. Okay, now we won't have time to do all of these. So I'm just going to start with 2A, at least not today. We'll continue this discussion next class. So in the case of question 2A, it says, what is the pH of each solution, A, B, and C? So we're talking about A in this case. After titrating 12.00 mils of 0.0500 m sodium hydroxide with 6.00 mils of a 0.200 m benzoic acid solution, and they gave you the Ka value for benzoic acid, which is 6.28 times 10 to the minus 5. Okay, so again, I'm going to need more space to do this problem. So let me go here. Let me get rid of this. And let me get rid of that. Okay, so the first thing I would do is I would find the number of moles of the sodium hydroxide and the benzoic acid in each case. So the first thing I would do is write down here the number of moles of sodium hydroxide is equal to the volume, which is 12.0 mils, multiplied by this conversion factor to convert it from milliliters to liters, and then I'll multiply by the molarity. So the molarity of the sodium hydroxide is 0.000 moles divided by 1 liter, and I'll work that out. And when I did that, I got 6.00 times 10 to the minus 4 moles, all right? And then I'll do the same for the benzoic acid. I'm just going to use HB to represent benzoic acid. So the volume is 6.00 mils times 1 liter over 1,000 mils. And then I'll multiply that by the molarity, which is 0.200 moles over 1 liter. And that gives you 1.20 times 10 to the minus 3 moles. Okay, so now we have the moles of each of these formulas or compounds. The next step is to write down the equation for the reaction between the base, which is sodium hydroxide, and the acid, which is benzoic acid. So you're going to end up with NaB plus H2O. And then initially, I'm going to write down the amounts of each of these underneath their respective substances. So in the case of sodium hydroxide, that would be 6.00 times 10 to the minus 4 moles. And in the case of HB, that would be 1.20 times 10 to the minus 3 moles. And then this would be 0, and we don't need to concern ourselves with H2O. As far as the changes are concerned, we need to identify which of these two would be the limiting reactant, which would obviously be the sodium hydroxide. So I'm going to put minus 6.00 times 10 to the minus 4 moles, because all of it will be used up. And because of the 1-to-1 mole ratio between those two, I'm going to put minus 6.00 times 10 to the minus 3 moles of that. And then over here, that will be plus 6.00 times 10 to the minus 3 moles. All right. So at the end of the reaction, you're going to have
I have a
0
question.
here. Oh, yes, ma'am.
Why did you switch it to -3?
Okay, what are you talking about?
You did minus 6.00 times 10 to the -3 moles under
Oh,
HB.
thank you. That should be minus 4. My bad.
Thank you.
Thank you. Thank you for pointing that out. Okay. So as I said before, that's 0. When you work this out, you're going to get, let me see here. You're going to get 6.00 times, whoops. You're going to get 6.00 times 10 to the minus 4. And here you're going to get plus 6.00 times 10 to the minus 4, right? Okay, so guess what? At the end of this reaction, The only two things remaining will be the acid and the conjugate base of the acid. In other words, what do we have here? What do we call a mixture of a weak acid and the conjugate base of the acid? We just did it earlier. Huh? Anybody? What do we call a mixture of a weak acid and the conjugate base of that weak acid?
A buffer.
Exactly. And what equation do we use to calculate the pH of a buffer solution?
Yeah, Henderson-Hasselbalch.
Henderson.
Exactly. So let me remind you of the Henderson-Hasselbalch equation. It's pH is equal to pKa plus log of the concentration of the base, which is B minus, divided by the concentration of HB. So my question to you now is, what's the concentration of B minus? Let me give you a hint. I'm going to circle the hints for you. I'm going to circle that. I'm going to circle this. And I'm going to circle this. You're going to need those numbers to help you to calculate the concentration of the conjugate base.
The 0.05 molar.
I'm sorry?
0.05 molar.
Okay, well, how do you get the answer? I don't think that's right anyway. Hold on, wait a minute. Yeah, I don't think that's right anyway. How do you get the concentration of B minus? The concentration of B minus will be equal to the moles of B minus divided by the volume of the solution. So what's the moles of B minus? Oh, here's another hint right here. Well, come on, it's staring you right in your face.
(6.0 times 10 to the negative 4 moles.
Exactly. And what's the volume of the solution? Let me do that here. Volume of solution. What is the volume of the solution?
18 milliliters.
Exactly. It's 12.00 moles. I mean, not moles, mils plus 6.00 mils. And that's equal to, as you correctly said, 18.00 mils, right? So basically, you're going to divide by 18.00 mils. And of course, you have to convert that to liters. 1 liter over 1,000 mils, all right? And according to my calculation, this works out to be equal to 0.0333 M. And guess what? This is also equal to the concentration of the acid, right? Because we have these two same numbers here for the acid and the conjugate base, and you have to divide each of them by the same volume, so they're going to be the same. So what does that tell us about this equation? the Henderson-Hasselbalch equation in this case.
pH equals KPA or PKA.
pKa, exactly. pH is equal to pKa. So basically, all we have to do is find the minus log of the Ka, which according to the question, that's equal to minus log, well, the Ka is equal to 6.28 times 10 to the minus 5. And that gives you the pKa, which is 4.20. And that's how you do that. All right. Okay, any questions about that example? Any questions? Okay, let's take a break. And then we get restarted at 1 o'clock and then we'll finish up. All right. Okay, so what I've decided to do is that I will leave the other parts of that question. Let me go back to, okay, so we did the A part for number 2 in assignment 5. So I'm going to leave the B part for you to attempt. We can come back to it next class, but I want you to try on your own, the B part, as well as the C part, all right? So I'm going to leave that for you to try it out, and then we can discuss it next class. I just want to introduce to you the concept of solubility product. I think I'm just going to stick to this page and call it a day. So when it comes to solubility of sparingly soluble compounds, so we're talking about those compounds which we generally regard as insoluble. What you'll find is that when you add them to water, there will be a very small amount of that compound that will actually dissociate and go into solution, all right? A good example of that would be silver chloride. As you can see, the equilibrium of that particular dissociation is shown here, where the silver chloride will dissociate to form silver ions and the chloride ion. And therefore, as a result, because it's an equilibrium system, we can write down an equilibrium expression for it, where the equilibrium constant would be equal to the concentration of the silver ion times the concentration of the chloride ion. And you'll notice that the silver chloride itself does not appear in this equation because, as we learned earlier, about 2 chapters ago, we learned that any solids or pure liquids present in equilibrium will not change their concentration. The concentration will be constant, in other words, so therefore they will not appear in the equilibrium expression. So this is the equilibrium expression for this dissociation. And there's a special name given to this equilibrium constant. It is called the solubility product constant, KSP, all right? So that's the constant, that's the equilibrium constant when it comes to the dissociation of sparingly soluble ionic compounds. And just to give you some examples of different compounds of that same type, you see the corresponding dissociation equations along with their respective KSP values or KSP expressions, all right? And of course, you recognize that in each case, the concentrations are raised to the power of the coefficients in the balanced equation for each of these ions, all right? Now, one utility of understanding the role of KSP is that we can make certain predictions as to whether or not a particular solid will precipitate out of solution. And that is based on comparing the Q value to the KSP, right? So if the Q value, now remember, Q would be the product of the concentration of the ions, regardless of whether or not the system is at equilibrium, all right? Q, in this case, is less than KSP. If that's the case, then basically you're going to end up with an unsaturated solution, right? So in other words, there's no precipitate that would be formed, all right? So that's going to happen when Q is less than KSP. Now, if Q is equal to KSP, then the solution will be saturated, all right? That means that, again, there'll be no precipitate form, but that's a maximum concentration of the solute in the solution. And then now we get to where Q is greater than KSP. If Q is greater than KSP, then in this case, the solution will be supersaturated, which means that it's going to be very unstable. And therefore, what will happen almost immediately is that a precipitate will form, all right? So basically, we're going to see some examples. In fact, the assignment questions in assignment 5 later on will actually deal with this sort of situation where you have to make predictions as to whether or not a precipitate will form. Now, the next slide I'm going to show you is basically a list, and this is by no means an exhaustive list of different sparingly soluble ionic compounds and their corresponding KSP values. And what you'll notice immediately, or what should come to you immediately when you look at this list, is that these KSP values are very small, all right? That is typical of these values, okay? In fact, the largest one I see here is this one right here, lead 2 chloride. Its value is 2.4 times 10 to the minus 4. And I think the smallest one I can see here is the one for bismuth sulfide, which is actually the smallest one is aluminum hydroxide, from what I can see. No, actually, copper 2 sulfide, all right? Its value is 6.0 times, oh, okay, I'm messing up. Here's the smallest one. I think this is the actual smallest one. Silver sulfide, which is 6.0 times 10 to the minus 51. So that just gives you an idea as to the type of numbers that we're dealing with, all right? So that's typically what happens in the case of KSP measurements. And as we're going to see shortly, you can do calculations of several types if you want to determine the solubility based on the KSP or vice versa. In fact, this flow chart here, or these two flow charts, shows you some typical calculations involved when it comes to using KSP. So for example, if you know what the solubility of the compound is, which is the number of grams of solute dissolved in 1 liter of solution, then you can convert that to molar solubility, which is the number of moles of solute dissolved in 1 liter of a saturated solution. Then you convert that to the concentrations of the cations and anions, and that, of course, is dependent on the stoichiometry of the dissociation. And then from there, you can determine the KSP, all right? So that's how you get from the solubility of the compound to the KSP. And basically, this other flow chart here is showing you the reverse, all right? Going from the KSP to the solubility. So in the assignment that we'll be looking at, or continue to be looking at next week, you're going to see some examples of that type of calculation, such as this one right here. So let me go through this quickly and then we call it a day. Question is asking, what is the solubility of silver chloride in grams per liter? That's a dissociation. This is the KSP expression or KSP value. And we set up our ice table. Now, in this case, we won't be concerned with the silver chloride because it's a solid. So initially, you would have no silver ions and no chloride ions. Now, the change in this case, we're going to call it plus S. S stands for the solubility, the molar solubility. And the same will be true for the chloride. So at equilibrium, these would be the concentrations of the silver ions and the chloride ions. So therefore, we write down the KSP expression, which is KSP is equal to the concentration of silver ions and chloride ions. And then we plug in the S values here. And what do we get? KSP is equal to S squared. So therefore, we can determine S, which is equal to the square root of KSP. And then we put the numbers in, and we end up with S equals to 1.3 times 10 to the minus 5. Now remember, this here is the molar solubility. The question is asking for the solubility in grams per liter, right? So basically, to do that, we take the molar solubility here and we convert it to grams per liter by multiplying by the molar mass of the silver chloride. And the answer in this case works out to be 1.9 times 10 to the minus 3 grams per liter. All right. So that's basically how that is done. Okay, we're going to stop here. Let me remind you that you need to watch the video or videos for chapter 5. I started off with discussing what I just discussed, molar solubility and titration curves and all that. Now, let me say that I've posted a couple of videos which show some examples. And I will admit it's a bit heavy on the calculations. Let me go here. So let me do this here. Modules, okay, modules. So let me publish that set of videos now, right here. Okay, so the videos are published now, right? And I want you to pay particular attention to all these videos here, which deals with pH calculations, right? These are all different examples, right, of the type of calculations where you try to calculate the pH of a solution at different stages of the acid-base titration. And I discussed indicators already. I discussed solubility product and precipitation. Well, in part, I don't think I finished doing that. And then, yeah, the solubility product and the common ion and pH effect. So make sure you watch all those videos. And if you have any questions, feel free to pose them next class, all right? Okay, so that's it. Our time has run out. So I'll see you guys on, oh, before I forget. Well, no, it wouldn't apply to you. I was thinking of something, but I'll talk to my lab class about that. Okay, so that's it for today, folks. So see you guys on Wednesday. All right, take care.
Real quick before you go, I had a question about the assignments, like writing on the assignments themselves versus like notebook paper, right? From now on, I'll write it on the assignment, but for assignment 4, I did not because I didn't realize that. So would you like me to, I can print out the actual assignment and then write the answers there on the actual assignment and then also submit my work on the loose leaf paper? Is that good?
Oh, all right, tell you what, I'll accept your, you know, what you have done so far for now, but for future reference, make sure that you do it on the original document.
Right. Assignment 5 and 4, it'll be on the original document.
Okay,
Thank you.
very good. All right, cool. Okay, so that's it, folks. See you guys on Wednesday. All right, take care.